Similar triangles. Now in mathematics, we learn that if we have two triangles that contain the same angles, let me call that triangle ABC and call that triangle PQR. And let's say that they contain angles A, B, C, and this one also contain the same angles. Then we know that these two are called similar triangles. And then we learn that the ratio of corresponding sides are equal. That means that if I orientate the two triangles so that the same angles point in the same directions, then this side corresponds to that side, this side corresponds to that side. So we call, say, these two the corresponding sides, or those two are corresponding sides. The ratio of the corresponding sides means, for example, AB over PQ. So this is a ratio of these two corresponding sides. Now, I can have another two corresponding sides, AC and PR. Right? And the mathematics of similar triangles tells us that these two ratios are equal. So in this session, I'm going to prove this. Now the proof for this starts with looking at a triangle Okay, think about this as a triangle that is not related to the above two. Just think of it as a separate thing. Now in the step 1 of this proof, okay, there's something we must show. Now suppose that I have a triangle, I'll call that ABC. So let's suppose that it has nothing to do with the previous triangle for now. And consider a line through the triangle, in the triangle, that is parallel to one of the sides. Then there is something called an intercept theorem in mathematics, which says that this parallel line, or this line that is parallel to one of the sides, that this line divides the other two sides into the same ratio. Now let me call this DE. Same ratio means, for example, if you look at the ratio AD to DB, that's one ratio for one that AB is divided into, and then AC is divided into the ratio AE over EC. Okay, so this line divides AB into this ratio, and it divides AC into that ratio. And the intercept theorem says that these two ratios must be equal. In the first step, we must prove this. Now we can probably see, looking back up at that, where we are heading. If we can prove this, it then becomes fairly straightforward to show that this is the case. But this is the tricky bit. Okay, this looks like the kind of thing that we would normally just take for granted when we do questions on similar triangles. But how can we actually prove this? The way to do it is to think about drawing two triangles in this figure. This is one triangle, this one, BDE. And the other triangle is this one, DEC. The way is to first realize that the areas of these two triangles are equal. Okay, and then relate these two triangles to the sides DB and EC, DB and EC that are involved in the ratio. So let's first establish that those two triangles are equal. DEB, triangle DEB, area of this triangle is equal to area of triangle DEC. Let's think about why. It is because if we look at DE, which is a common side of the two triangles, if you think of DE as the base of these two triangles, Now it's usually easier to have the base at the bottom, so let me turn this around. If D is the base, okay, then you can see that these two triangles, this one and that one, would have the same height, because both the corners B and C are along the same parallel line. So that if you measure the height of B to the base, the vertical height of B to the base, or the vertical height of C to the base, they would be equal. So therefore, these two triangles have the same base and the same height. Therefore, the angles, the areas must be equal. So we have just shown that. Okay, so let me write down this conclusion. Okay, that these two triangles are equal because they have the same base, which is DE, and same height. So now that we have established that, let's then see how to relate it to these two ratios. Now these two ratios involve AD and AE. So AD and AE. Now in the next step then, we look at these two triangles, ABE and ADC. And we notice that the triangle ABE is also equal to the triangle A, so ABE, ADC. Why is that? Now, you see, the triangle ABE, you can think of it as made up of two triangles, ADE and DEB. So this is really triangle ADE, the top one, and triangle DEB. Now that one, ADC, is made up of ADE and DEC. So if you compare those two, you see that the triangle ADE is common. It's the same. Okay. Now the other two parts, which is this part and this part, we have already seen from the last step that they are equal. Right? Those two are equal. So therefore, this must be true. So area of this is equal to this because this is equal to this, basically. Okay. Now, so let's carry on. Since these two triangles are equal, let's think about the sides of the two triangles, this side and this side. Alright, these are the two sides that are divided into this ratio that we want to show. So we have this area here. So the area of a triangle, as we know, is half times the base times the height. Hope you have seen this part of the writing that I wrote down just now, where I showed that this where I showed that these two triangles, that one and this one, are equal because this is common and this part is equal to that part. So that's what this is about. Now, in order to carry on, we then need to make use of this, what we know about the area of a triangle, that it is equal to half base times height. So in this case, let's go back to those two triangles. Now that we know that this is equal to this, equal as in that the areas are equal, not as in the sides are equal. So if we think about those, this triangle and this triangle, think about the ratio of the areas of ADE and ABE. So if I take the area of A, triangle A, if I take the triangle ADE area and divide it by the triangle DEB, if I divide those two triangles, the answer must be the same as dividing the base, dividing AD by DB. Okay, I'm skipping the step a bit. Let me write this down anyway, DB. And that's because if I look at those two triangles and I think of this side as the base, then the height of this triangle is given by perpendicular from E to this base. Okay, let me call that H1. Alright. And I know that the triangle ADE, its area is given by half of this base times this height. Half of the base AD times the height H1. DEB would be the half of the base DE times that height. Okay, so that's equal to this, and if we then cancel the common factors, we are left with AD over, oh sorry, that's dB, right? Left with AD over dB, which is this. Now likewise, we can repeat that for this side and for these two triangles. Okay, so we would have that the triangle ADE divided by the triangle DEC is equal to, right, the top triangle. Now this time I'm going to take that as the common base, or the side for the base of those two triangles, and then in this case the height would be obtained by this perpendicular from D to the base, and let me call this height H2. So the triangle of ADE has the area half times this base AE times the height H2. Okay, and DEC has the area of half times the base EC times the height H2. Cancelling the common factors, we have AE over EC. Okay. Now looking back at this result so far, we have obtained these two ratios. Alright, we have obtained that the ratios of the areas are equal to those two ratios, alright, which are the ratios of the sides that we wanted to show are equal. So we have obtained relations between the separate ratios of the sides with these two triangles. Now and finally, we want to say that those two must be equal, because obviously the top part is the same, and the bottom part DEB and DEC are those two. DEB and DEC, we already know they are equal from this result just now, because they have the same base DE and the same height. Okay, so therefore these two are equal, and therefore those two must be equal, which is what we set out to prove down here. Finally, let me write it down. Because these two, triangle DE, right, because those two, triangle DEB must be equal to triangle DEC, therefore those two ratios AD over DB, AE over EC must be equal, okay, which is what we set out to prove. So that's the first step, and that's the intercept, called the intercept theorem. So let's summarize this result. Okay, this result says that right, a line parallel to one side of triangle, just use a notation, a symbol for that, divides the other two sides in the same ratio. And what we have shown in the proof is that we have shown that AD over DB is equal to AE over EC. Okay, this is what I've written down in case you could not see it. Okay, but it does not just have to be AD over DB equals to AE over EC. Since we already know that they are in the same ratio, we can also take the ratio of, for example, AD over AB. Alright, so instead of doing AD and DB, I can do AD over AB, and this must be equal to AE over AC. So from what we know about ratios, we can also have this relation. So that completes the step 1. Let's now go on to step 2. And step 2 will complete the proof for the similar triangles. We want to show that if I have two triangles that contain the same angles, then the ratio of the corresponding sides are equal. Now if you look at what I've done here, I have shown that when I have this triangle with a parallel side, okay, the ratios, these ratios are equal. Now if you are familiar with exercises on similar triangles, it would now look like this has pretty much proved it. Okay, it pretty much proved that the corresponding sides have the same ratio. But we have to be careful here to make sure that every step is clearly spelled out in the proof. So for example, if you look at this and this, we have described this as a parallel line, a line parallel to one side of the triangle. And these are described as two separate triangles containing the same angles. So in this step 2 then, we should relate those two triangles to this one triangle with a parallel line. Now you can clearly see that this parallel line forms a smaller triangle inside the bigger triangle, and it would look pretty much like that smaller angle. So in order to make use of this, we would simply take that smaller angle and move it into the bigger one. I'll call that PQR. So let me draw it out here. Copy out PQR. That's A, B, C. Now moving ABC into there means that it now fits, I'll fit the angle A into that corner, and BC would now be a line along here. Okay, so I'll still call this BC. So A has moved into that point, and those two angles are the same as those two angles, B and C. Now, so in order to make use of this intercept theorem, which is about this parallel line, I would first need to say that because we were not given initially that those two lines are parallel, we will need to show that or explain why they're parallel, even if it looks obvious. Right? We make use of what we are given when we prove something. So we are given that those two angles are equal and those two angles are equal. Now, if those two angles are equal, okay, that actually means that these two lines must be parallel. And that's the property of corresponding angles. Alright, so if these two lines are parallel, those two angles are equal because they are corresponding angles. So conversely, if those two angles are equal, these two lines must be parallel. So BC would be parallel to QR. So that's the first step in this step 2. And the next step, right now that we have explained why these two lines are parallel, we can now make use of the intercept theorem from above, which says that a parallel line divides these two sides into the same ratio. So therefore, from the intercept theorem, we have that AB, the ratio AB to PQ, and the ratio AC to PR must be equal. And since these are the ratios of the corresponding sides, we have just proved this relation for similar triangles. So this completes the proof.